Okay, so for the following fluid mechanics problem, it reads, water is pumped from the large tank shown in diagram A below. The entrance to the pipe section is sharp-edged, and the pipe is cast iron with a total length of 2 meters. Flow within the pipe is observed to be fully turbulent. The relationship between volumetric flow rate and the actual head rise is provided in pump specifications and is shown in diagram B. Okay, so it's a three-part question. Part A, determine the volumetric flow rate for the system. B, show that the observation of fully turbulent flow was correct. And C, if the pump is 70% efficient, determine how much power must be supplied to the pump. Okay, so for part A, they want us to determine the volumetric flow rate. And in fluid mechanics, we have the variable Q, which stands for volumetric, which stands for the flow rate. And the volumetric, it means it's a volume at a rate. So the unit for volume is cubic meters, and the rate is just per second. Okay, so that's part A. Part B, they want us to verify that the observation that it has a fully turbulent flow is correct. And they tell us here, flow within the pipe is observed to be fully turbulent. So until it gets to this open volume here, then we have turbulent flow. And in order to verify that it is turbulent flow, we need to use Reynolds number, which is equal to rho VD over mu. So this will, when we plug in everything in, it should just give us a number, and it should be in one of the three flow regimes. And the first one, if the number is below 2000, then it will be laminar flow. If it's equal to 2000, then it's transitional between laminar and turbulent. And obviously above 2000 will be turbulent flow, which is what we want to find. A number that's bigger than that. So rho is the density of the fluid. In this case, it's water. V is the velocity of the fluid traveling in the pipe, and here we want to use V going out of the shaft. D is the diameter of the pipe, and mu is the dynamic viscosity of the fluid. So rho and mu we can find in one of the tables at the beginning of the book. Okay, let's see. So, and then part C, they tell us that we have a 70% efficient pump, and we must determine the power needed in order to have the same flow rate. So the power required is we denoted by W dot, which the dot is just it means per second. So W is just energy, joules per second, and this is watts. Unit is watts. Okay, so for part A, let's see. We want to use, we want to find Q. So how can we find Q? We want to use the energy equation, or Bernoulli's equation. So the equation goes P1, pressure 1, rho G divided by rho G, plus V1 squared divided by 2G, plus Z1 plus the head rise, HA, is equal to P2 over rho G, same thing, but with a subscript of 2, plus V2 squared over 2G, plus Z2 plus head loss. Now I want to explain what this and this are. So here they give us the pump head here, HP in meters, and we know that HP is the net head rise into the pump, and that's just synonymous to saying the head rise. So we'll just denote it by HA. And this is equal to HS, which stands for the shaft work head, minus HL, which is your head loss. Now this term here, these two, it means that it's the amount of energy per unit weight of fluid added to the fluid in order to raise the water that is traveling in the pipe to a certain height. And then you subtract your head loss, which are losses due to friction. So, and if you, let me show you here so you can kind of see it a little bit better. I think it's in the centrifugal pump section. Okay, it's all the way over here. Here it is. So I just kind of want to show here. What I said was the energy required to move water from point 1 to point 2. I want to move it up 2 meters. So that would be a HI, the theoretical energy required in order to move from a point, in order to move the water from here to here. But realistically, the head rise, it's not just the ideal HI. You have to take into account the losses due to friction of the water traveling in this pump. So that's why we subtract the HL, which are the losses due to friction. And all it is just a pressure change equivalent to a height change in a static fluid. Okay, so that's why you kind of see a meter unit, because like I said before, it's the amount of energy. So what is energy? Energy, we'll say, is like joules per unit weight of fluid. Per the unit weight, let's call it W here. And so what is energy? If we try to have this expressed in a different way, Newton meters. And then if I say I weigh, if I'm 190 pounds, let's say I'm 190, just for example, times the acceleration due to gravity, I'm going to put, which is 32.2 in standard. And that's just going to give me the force that I put, whatever it is. That's the force, my weight on the floor. So the same thing here, the force, W is N. So that's why they cancel, and you see the head loss and the head rise expressed as meters. Okay. All right, and then further simplifying, here I have, oh, and before I continue, I want to establish a datum, a reference point. And this will be my reference point because I want to establish what the subscript 1 and the subscript 2 are going to be at. So subscript 1 will be at the surface here of the water, and this little triangle means that it's open to the atmosphere. Okay, and then the second point will be at the exit of the shaft here. Okay, so P1 divided by rho g. Well, if it's open to the atmosphere, just as a general rule, this will go to 0. Okay, so this is open to the atmosphere. P2 at the exit, doesn't matter what the velocity is here. P2 will also go to 0 because it's open. Okay, now V1 here, and let me set this aside. V1 is, well, they tell you here, water is pumped from the large tank. The key word here is large. So it's a large enough tank that the water at this height it's going very slowly, so slowly it's negligible, and it goes to 0. Now here will be a different case because the opening is much smaller than this area here. Okay, so this goes to 0. Z1, well, we chose this as a reference. This will be 0, height of 0. So it tells you here 6 meters. So Z1 equals 6 plus the head rise is equal to v2. Now this is a velocity that we want to find, because we want to, if we can find this velocity, we can try to get to q, because q, as we know in general, is equal to velocity times the area. And why is this? If we want to verify it's a volume per second, well, velocity units are meters per second. If we multiply times the area, squared meters, we get cubic meters, and the exponent 1 plus 2 per second, and we have volume per second as we found earlier. Let's see. So we have v2 squared divided by 2g plus z2. Well, z2 is conveniently placed at the reference, so the reference is just 0 at a height of 0, so it goes to 0. And we have h loss. Okay, now the head loss are your losses due to friction. And your losses due to friction here, well, we have, it's broken into two parts. It's broken into the major losses and the minor losses in the shaft. So when you have a major loss, it's just the viscosity that's impeding the flow of the water, the viscosity here, okay, because it's creating a, no, not the viscosity, sorry, it's the friction here on the shaft. It's kind of impeding the flow of the water. So major loss in the straight section of the pipe, and we call, let's simplify again, so I can expand the h loss into two parts, which is equal to plus FL divided by D. That's just your equation for the major loss. Okay, and then plus the minor loss, K L V squared divided by 2G. Okay, so F is a friction factor that will depend on Reynolds number. If we can find, if it's turbulent here, then we can, or depending, it will depend, F will depend on the roughness of the shaft and the length and a bunch of the stuff we'll see in a little bit. Okay, so we're gonna find this. L is just the length of the shaft. D is the diameter of this part. V squared is the velocity, which we don't know. We're further trying to simplify. And KL is a coefficient that depends on the type of minor loss you have. So if you have like a change in area here as the water comes in, then that's a minor loss. If you have a valve, that will also create a friction that will give you a little bit of minor loss. Okay, so let's see. Let's first try to find the KL, the coefficient, the loss coefficient for this part, because here we have a change in big area to a small area. So if we just try to have it here, and I already have it, as you can see here, we have a big area to a small area, as we see here, and it tells us to find, if we want to find the KL, well, we just divide A2 divided by A1, and we just follow the line, and wherever the line ends the height is gonna be the KL. So A2, well, we don't know A2, but let's see. A2, like we mentioned, this is on this part in the shaft. So we have a diameter of 0.07 meters. Okay. Area can be expressed as pi divided by 4 times diameter squared. Okay, and that will just give us, if we try to do it here, times pi divided by 4. And we get 0.00384. Okay, that's area 2. Okay, and then area 1. Oh, this is area 2. I was making it confusing. This is area 2. And then area 1, well, we don't know the area, but it's big enough. We'll just call it like, I don't know, like 7. So if I had to call this part 1 extra meter, I'll just add the 6. That's the diameter. So I have like 7. Like this area is the one I want to find, this part. So 7 squared times pi divided by 4, 38. So if, as you can see, the previous number, A2, divided by the bigger number, is a very, very small number, 9.99 times 10 to the negative 5. And we just kind of follow that here. Here's 1. We got to go way, way down here. And it's close enough to the 0. Then we can just go up to this part of the curve. And it looks to be at 0.5. So KL will be 0.5 for the minor loss in the sudden change, in the sudden contraction here. Okay, so again, simplifying, and I'll move the 6 to the right side. Rise is equal to V2 squared, or 2G, plus F. And then L, what is the length? It's 2 meters, divided by 0.07 meters. Okay. Let's see, and then V squared over 2G plus 0.5, and just further simplifying, this is a subscript 2 by 2G and minus 6. Now, why am I isolating head rise? Is because here they give us the pump head, which, like we said, this is equal to this. And they give us a curve equation for the head pump. Okay, so this, if we can try to isolate this variable and equal it to this equation, well, maybe we can find, maybe we can try to find a way to isolate V. Okay, so here we have a few common terms, and I'll just factor out this term because we see it in common. V2 squared, so HA is equal to 2 squared over 2G, and then times itself. Okay, so I can bring it out. Plus, and then 2 divided by 0.07. We get 28.571. 0.571 times F, and then plus 0.5, and the minus 6. Okay, so we have that. We can add the 1 to the 5. So we get, if you can see it here, HA is equal to V2 squared over 2G plus, oh wait, actually factored, 1.5. It's the same thing, I just added the 1 and the 0.5. So 1.5 plus 28.5714. Okay, and then minus 6. Okay, perfect. Now, further simplifying, I don't think I can do anything else but just pretty much like multiply that 2 times the g, which is the acceleration due to gravity. So now I can try to use this equation I mentioned. Yeah, head pump is equal to 20. So I can see it here, 20 minus 2000 Q squared. And that is equal to what we found, which is V2 squared over 2G times 1.5 plus 28.5714. Just to get a little bit closer answer, we'll round that at the very end. Minus 6. Okay, so that's what we have here. Let's see. Now, how can I find V or Q? If I think about it, they don't give us any other relationships here, but we do know the diameter of the shaft, and maybe we can try to isolate Q to try to plug in, because we see Q here and we don't have any other Q's. Okay, so just sub it in. So like I said, if we have is general relationship Q equals VA, well, they give us the diameter and we can find the area. So V times, and that's V2, V times pi divided by 4 times 0.07 squared. Okay, and that's what we want to try to plug in here to try to isolate V. Okay, so let's see, pi divided by 4 times 0.07 squared, and we get 0.00384, I don't know, 8 minus 1. It doesn't have to be that exact, but I just try to do it this way. Okay, so that's equal to Q. Oh, and the V, very important. And that is equal to Q. Okay, now this Q we can plug in here. So 20 minus 2000, 0.003848 V squared, okay, is equal to this, same thing, we're just simplifying. Okay, so that number squared times 2000 and 20 minus, you know what, I'll leave that number and I'll bring this guy to the left side so I can add it to the 6. 20 minus 20, they cancel, and I get negative 0.02962 V2 is equal to, you know what, I think it's time to simplify, because we're getting the V terms and then we can add the V terms together. So we have, let's see, 1.5 divided by 2 times the acceleration due to gravity, which in this case G is equal to 9.8 meters per second squared, because we're in metric, okay, metric units. So 2 times 9.8, and we get 0.07653. Okay, V squared. Did I square it? Let's see. Oh, yes, I gotta square this term. Forgot. I squared this term, but I didn't square the V2. Okay, V plus, and this is the F. Don't forget to bring the F here, which is what we found earlier. This guy, just bring it in. Forgot to bring the F. Okay. So we have 28. And you know what? I'm just going to find it here. Where's the 28? 28. Let's see. Times, or divided by 2G. 2 times 9.8. and we get 1.4577 F V squared minus 26. I don't know if you can see that. Okay, let's see. Now I can bring this guy to the other side to add it. Or I'll add this guy. I don't like to have negatives on the left side. So 0.07. Okay, plus 0.02. Where's the 0.029? There we are. And we get 0 is equal to 0.106. 151 V2 squared plus 1.4577 F V2 squared. And then we'll add the 26 a little bit. So 26 is equal to okay, let's see. Can I add these terms? I can't add them. So I have 0.106. I see. I think I gotta find F in order to find V. So the friction factor. In order to find the friction factor for the major loss, I need to go and use the Moody diagram. So where's the Moody diagram? Here it is. So the Moody diagram here is given. And now, since we can't use Reynolds number, rho VD over mu, because we're missing the V value, but remember in the problem statement, they tell us flow within the pipe is observed to be fully turbulent. So fully turbulent, only in this control volume that I put it in the box here, okay, is observed to be fully turbulent. And here in the Moody diagram, well, if we can't use the V, we can look at this line that tells us wholly turbulent flow. So it should work with that line. Now, how can we, where do we want to find ourselves in? Well, here they give us, it's like a Greek letter, I forgot the name, over D, epsilon over D. So if we use that, now epsilon, it stands for the roughness of the pipe. So here they tell us the pipe is cast iron. So cast iron, I look it up on the table. Here we are. We're in meters. So we get 0.26. E for iron, 0.26. Okay. Let's see. So the formula, I'll go back to it again. Where is it? There we are. So 0.26, they tell us E over D, and the diameter is 0.07. Oh wait, I think I made a mistake. Not 0.26 meters, it's in millimeters here. So millimeters, 0.26 times 10 to the negative 3 is actually in meters. And then we find it out. Let's see, 0.12326 divided by 0.07. We get 0.00371. Okay, and then that value, we just plug it into the Moody diagram. Oh, come on, keep losing it. Okay, so 0.0037, 2 zeros here, right in between the 0.002 and the 0.004. Let's see, 0.003, 3, so it's like a little bit past the third, past the middle, right around here. And it looks to be, oh, can't see, as you can see here, 0.0037. Okay, it's a little bit past half. So let's just say 0.028. It looks to be like 0.00 or 0.028. Yep, we'll use that F value. Okay, 0.028. Okay, and then let's continue. Now, if we can sub it in, get 26 is equal to 0.1065151 V2 squared plus 1.4577 times 0.028. And now we can finally add the, because this is like an x and this is like an x, we can add together. So we have 1.45, let's just find it, times 0.028, is that the right number? Yep. And we get that number. So same thing, 0.04081 V2 squared plus this number, just bring it down so as to not make any confusion. Okay, we add them up, this one and this one, plus 0.106, it's right here. We get 26 is equal to 0.14696 V2 squared. Divide the 26 by that number, by this constant. 176 is equal to V2 squared. Take the square root of both sides, and V2 is equal to, let's see, 13.301 meters per second. Oh, 13.301 meters per second. Okay, finally, we found the velocity. Now, the velocity in the exit of this pipe, V2. So now we can use the formula Q equals VA. And notice we found it earlier. We just have this number times V. So we'll just replace it. We'll just do this times, let's see if I can find it, 0.0038. Is that it? 348. 3848. There you are. And we get a volumetric flow rate of 0.0511 cubic meters per second. And as I mentioned, the units match, so it should yield cubic meters per second. Let's see. So that is part A. We found the volumetric flow rate. Now part B is asking us to verify Reynolds number. And now that we finally found this velocity, now we can just plug in and it should yield the statement. It should verify the statement that the flow here is turbulent in the pipe. Okay, so let's see. So rho VD, Reynolds number, is equal to rho VD over mu. So rho, if you don't know rho, I know it's 999 cubic or kilogram per meter cube because it's a density. But if you don't know it, you just find it here at the beginning of the table of the book. Dynamic viscosity. Nope, it's oh, this is in standard. I need metric. There you are, 999 kilograms per meter cube. kilograms per cubic meter, I should say. Okay, times the velocity. Well, we found that out here, 13.301 meters per second. The diameter they give us is, what is it again? 0.07 meters divided by the dynamic viscosity of the water, 1.12 times 10 to the negative 3, and the units are Newton's second per square meter. Newton second. Is that it? Sorry. Newton second over square meter. Okay. So as you can see here, and just to confirm again, the units should cancel. We have meter and the meter, 2 meters, cancel with 2 meters. We have, let's see, this divided by seconds is simply, let's see, this goes, we have kilograms, I'll just make it again, kg, m, then cubic meters, then we have square meters, this goes up top, we have Newton second, okay, and we have a second. So let's see, we have meters, 4 meters on the top, 3 meters on the bottom, kilograms, Newton, and then second squared. So all this cancels, leaving a 1. Kilogram meters per second squared is a Newton. And Newton divided by Newton is just 1. So that's what I said at the beginning, where it should yield a dimensionless number, dimensionless unit, which is just 1. And now we just got to multiply it out to verify it's above 2000 to see if it's in the turbulent flow regime. 999 times 13.301. Let's see, times 0.07 divided by 1.12 times 10 to the negative 3, and we get 830,481.1, and that is way above 2000. So it is indeed turbulent flow. Okay, and then part C, let's see, part C, it's asking us to find the power required, and here, no, what is it asking us? Determine how much power must be supplied. So we need to find the power required. Like I said, it's by this variable, meaning power. Is the formula is that you need is the power gained by the fluid, and that is denoted by rho g h q divided by nu, the Greek letter nu. Okay, because the power required is always going to, in this case, is going to be a little bit less, because when you divide something by like a percentage, it's going to give you a little bit more, because you have to compensate due to the efficiency that is lower than the 100%. So that's why this number should blow up a little bit more, or not blow up, just increase. So let's see. Rho is, like I said before, 999 kilograms per cubic meter. G is 9.8 meters per second squared. Acceleration due to gravity. H, Oh, H. We don't know H, but we do know what it stands for. H is H. What is it again? The pump head. And it's given by the equation 20 minus 2000 Q squared. And we just found out what Q is. And Q is equal to 0.0511. So we just sub it in. 20 minus 2000. Where is it? Oh, here it is. In the calculator. We just square it. And then we simplify. Times 2000. So 20 minus this answer is H. And that H, again, like I said, is in meters. Road, oh, Jesus, 999, 9.8 times 14.75 meters is your head rise. So what that means here is that the energy that you put in the fluid here is going to make, if it were to travel upwards, it would travel up 14.75 meters. Like I gave you in this example on 698, I think. I last saw it. 698. So what this means is here the energy required to lift the water from here to here will give you enough energy to lift it 14.75 meters at that flow rate. Okay. So then, and then Q, we found Q was 0.0511. And the nu is the efficiency. They give us the efficiency, which is 70% efficient. So if we put it in decimal notation, we get 0.7. Okay. Let's see. Oh wait, this is the power. The power required. So 999 times 9.8 times 14.75 times 0.0511 divided by 0.7, and we get, is that right? I think I messed up somewhere. Let me try it again. Let's see. So 0.05. Is that the right formula? Which one is the right formula? Let's see. Rho GHQ. $20 minus that. Okay, 14.75. I'm just verifying that the answer is correct. Times 999. Times 9.8. Ah, there we go. I must have made a mistake in the calculator. 0.0511 divided by 0.7. There we go. And we get, finally, my mistake here, 10,548.56 watts of energy That's the power required, and which is also equal to 10.55 kilowatts. And that's it. So we found the volumetric flow rate required, the volume flow rate for this system going out here. We verified that the flow in this pipe is in the turbulent flow regime above 2000 in Reynolds number. And C, we found, given the 70% efficient pump, we found the power required to maintain that same Q, which is 10.55 kilowatts. And that's it.